Hello, friend. Welcome to another quiet journey through the cosmos. Tonight feels different, doesn't it? The air holds that particular stillness, the kind that makes you wonder about things larger than yourself. Maybe you've stepped outside and looked up. Maybe you've simply imagined it. Either way, the stars are there, waiting. They've been waiting longer than you know. Have you ever considered what you're truly seeing when you see a star? Not the science of it, not yet. Just the raw fact of light meeting your eyes across an ocean of darkness. It feels immediate, doesn't it? Like the universe is showing you its face right now in this very moment. But here's the gentle secret that changes everything you're not seeing now. You're seeing then. You're seeing yesterday, last year, centuries ago, millennia past. Every point of light is a letter from history, traveling through the void to find you. Before we drift deeper into this journey, if these quiet explorations bring you peace, you might like to stay a while. There's a small heart button below a subscribe option if you'd like more nights like this, and a bell that rings softly not to disturb, but to let the next quiet evening find you again when you need it most. No pressure, just an invitation. Now, let's begin. What you're seeing when you look at stars is time made visible. Light is the messenger, and distance is the delay. The star you're admiring might have changed, dimmed, even died, but its light continues traveling faithfully across space, carrying the image of what once was. In a very real sense, the night sky is a museum of moments, each star a frozen instant from a different era of cosmic history. Think about that for a moment. Right now, if you could see the star Sirius, the brightest star in our night sky, you're seeing it as it was 8.5 years ago. The light that's entering your eye right now left that star in early 2017. If you're looking at Betelgeuse, that red giant in Orion's shoulder, you're seeing light that departed around the year 1382 during the Ming Dynasty before Columbus sailed, before the printing press was invented. The star might have already exploded in a supernova. We wouldn't know. The news is still traveling. Scientists estimate there are somewhere between 100 billion and 400 billion stars in our galaxy alone. And there are roughly 2 trillion galaxies in the observable universe. That's more stars than grains of sand on every beach on Earth. Yet, when you stand beneath a dark sky far from city lights, you can see only about 5,000 stars with your naked eye. 5,000 out of billions of billions, and every single one of those visible points is a time capsule. The ancient Greeks knew stars were far away, but they had no concept of just how far. They imagined the stars were perhaps attached to a celestial sphere rotating around the Earth. It wasn't until 1838 that Friedrich Bessel made the first successful measurement of stellar parallax, proving that stars were fantastically distant, far beyond anything previously imagined. He measured the star 61 Cygni and found it was about 10 light-years away. At the time, people struggled to comprehend what a light-year even meant. A light-year isn't a measure of time, though the name suggests it. It's a measure of distance. Specifically, it's how far light travels in 1 year. Light moves at 299,792 kilometers per second. That's fast enough to circle the Earth 7.5 times in 1 second. In a year, light covers about 9.46 trillion kilometers. That's 9,460,000 kilometers. To cross just 1 light year would take our fastest spacecraft, the Parker Solar Probe, over 6,000 years. So, when we say a star is 500 light-years away, we mean the light we're seeing tonight took 500 years to reach us. The photons, those tiny packets of light, have been traveling through the vacuum of space for half a millennium. They have witnessed nothing. They don't decay or change. They simply move at the only speed they know from their birthplace toward wherever gravity and geometry take them. There's something deeply humbling about this. Every civilization throughout human history has looked up at essentially the same stars. The ancient Egyptians building pyramids saw the same Sirius. The Polynesians navigating by starlight crossed oceans using the same points of reference. Medieval astronomers, Renaissance painters, your grandparents, you all gazing at light that has traveled incomprehensible distances just to land gently on your retina for a fraction of a second. But here's where it gets even stranger. Light doesn't just travel, it struggles first. Before a photon can begin its journey to your eyes, it must escape the star itself. And that escape can take an extraordinarily long time. The light you see from our own sun, for instance, seems instant. We think of sunlight as a direct connection, an 8-minute beam from star to Earth. But those photons, before they could travel those 8 light minutes to reach you, spent anywhere from 100,000 to 170,000 years just trying to get out of the sun's core. The sun's core is a place of unimaginable density and pressure. Hydrogen atoms are crushed together so violently that they fuse into helium-releasing energy in the form of gamma-ray photons. These newborn photons try to escape, but they can't move freely. They're immediately absorbed and re-emitted by other particles. They bounce, scatter, zigzag, moving perhaps a centimeter before being absorbed again. This random walk through the sun's layers can take tens of thousands of years. Only when they finally reach the sun's surface can they fly freely unobstructed into space. So, the sunlight warming your face right now is ancient. Not 8 minutes old, but millennia old. The energy was born in nuclear fire when woolly mammoths still walked the earth, and it's only just now completing its journey to your skin. Different stars produce light differently. A red dwarf star, small and cool, creates photons slowly. Its core burns hydrogen at a gentle pace. These stars can live for trillions of years, far longer than the current age of the universe. Their light is faint reddish patient. A blue supergiant, on the other hand, is a cosmic bonfire. It burns furiously, creating vast amounts of light, but it exhausts its fuel in just a few million years. Its photons are born in violent fusion reactions, escaping in torrents. Massive stars don't just create light. They create the elements that make up everything around you. Carbon, oxygen, nitrogen, iron, calcium. Every atom in your body, except hydrogen, was forged in the core of a star. When those stars died, they scattered those elements into space. New stars, new planets, new life formed from that stardust. So, you're not just looking at ancient light. You're made of ancient stars. There's a beautiful irony here. The act of seeing starlight is in a way stardust recognizing its origin. The atoms in your eyes were once inside a star. The light entering your eyes came from a star. The universe is looking at itself, remembering where it came from. When you look up tonight, whether the sky is clear or cloudy, whether you can see stars or only imagine them, remember this: you're not just an observer, you're part of the story. The same forces that created those distant suns also created you. The same laws of physics that govern their light also govern your heartbeat, your thoughts, your breath. Light is patient. It doesn't hurry. It doesn't worry about whether anyone will see it. It simply travels across distances that would break your mind if you tried to truly comprehend them. And sometimes, after journeys lasting years or centuries or millions of years, that light finds an eye, your eye. And in that meeting past and present touch, some of the stars you see tonight will outlive our species. Others have already died their final light, still en route carrying the news of their ending across the dark. The sky is full of ghosts and futures all happening at once, layered across time, visible only because light refuses to give up, refuses to stop, just keeps moving toward anything that might witness it. You don't need to understand all of this to feel it. You never did. That's the gift of starlight. It asks nothing of you except to be seen. And in seeing it, you become part of something vast and quiet and unimaginably old. But where does this journey truly begin? Not in the space between stars, not even at the star's surface. The journey begins deeper in a place so dense and hot that matter itself becomes unrecognizable. It begins where photons are born, where light fights its first and longest battle just to exist. That's where we're headed next, into the heart of a star, where creation happens one collision at a time, and where a single photon's journey can take longer than all of recorded human history. Deep inside a star, there is no light. Not the kind you know, not the kind you could see, only pressure, heat, and violence beyond imagining. This is where photons are born, not in brilliance, but in chaos. And their first journey isn't outward towards you. It's a battle just to move at all. Imagine being trapped in a crowd so dense that every step forward pushes you backward. Every movement is blocked. Every direction is occupied. That's the reality for a newborn photon in the core of a star. It wants to escape, to travel at the speed it was born to travel, but it can't. Not yet. Not for a very long time. The core of our sun sits at about 15 million degrees Celsius. At this temperature, hydrogen nuclei are moving so fast that when they collide, they overcome their natural repulsion and fuse together. This is nuclear fusion, the engine that powers every star. When 4 hydrogen nuclei combine to form one helium nucleus, a tiny amount of mass is converted into energy. Einstein's famous equation, E equals mc squared, tells us that even a small amount of mass contains enormous energy. That energy is released as a gamma-ray photon, the most energetic form of light. But this photon born in fusion fire immediately encounters a problem. The star's core is not empty space. It's a dense soup of particles, electrons, protons, nuclei, all packed tighter than anything on Earth. The density in the sun's core is about 150 times that of water. A single cubic centimeter weighs roughly 150 grams. For a photon trying to escape, this is an impenetrable maze. When the gamma-ray photon tries to move, it travels only a fraction of a millimeter before it hits an electron or nucleus. When it collides, it's absorbed. The particle gains energy, vibrates, and then re-emits another photon, but in a random direction. This new photon might be slightly less energetic, perhaps an X-ray instead of a gamma ray. It travels another tiny distance, collides, again gets absorbed, re-emitted, redirected, over and over and over. This process is called a random walk. The photon moves, but not in a straight line. It zigzags, spirals, doubles back. Scientists have calculated that a photon in the sun's core might travel only about a centimeter before being absorbed and re-emitted. To cross the sun's radius of 696,000 kilometers through this dense maze takes an extraordinarily long time. The current best estimates suggest between 100,000 and 170,000 years. Some models suggest it could be even longer. Think about that. The light warming your face on a sunny afternoon was created before the last ice age ended, before agriculture, before writing, before civilization. A photon born in the sun's core during the Stone Age is only now reaching Earth. The sunlight you see isn't 8 minutes old. It's older than human history. But the sun is relatively small and stable as stars go. Let's compare it to something more extreme. Betelgeuse, that red supergiant in the constellation Orion, is about 900 times wider than the sun, and roughly 100,000 times more luminous. Its core operates at even higher temperatures, around 200 million degrees Celsius, fusing helium into carbon and oxygen. The photons created there face an even more chaotic journey. The star is so large and so turbulent that photons might take hundreds of thousands of years just to reach the surface, bouncing through layers of convective plasma trapped in a stellar labyrinth. And Betelgeuse is dying. Its core has already fused lighter elements into heavier ones, layer upon layer, like an onion. Iron is accumulating at the center, and iron doesn't fuse efficiently. It absorbs energy instead of releasing it. When enough iron builds up, the core will collapse in less than a second, triggering a supernova explosion so bright it will briefly outshine the entire galaxy. The photons from that explosion will travel freely, carrying the news across space. But the light we see from Betelgeuse right now The red glow, visible even to the naked eye, contains photons that fought their way out of that massive star over unimaginable timescales. Not all stars struggle equally. A red dwarf, the most common type of star in the universe, is much smaller and cooler than the Sun. Its core might only reach 5 million degrees Celsius. Fusion happens slowly, gently. These stars create far fewer photons, and those photons take a different path out. Because red dwarfs are fully convective, meaning their interiors are constantly churning and mixing photons get carried along with the moving plasma. They still bounce and scatter, but the journey might be somewhat faster. Yet these stars are so small and faint that even when their photons do escape, they don't travel far before becoming too dim to see. On the opposite extreme, consider a blue supergiant like Rigel, also in Orion. Rigel is about 79 times the radius of the Sun and roughly 120,000 times as luminous. Its core burns at ferocious temperatures, fusing hydrogen at a rate that will exhaust its fuel in just a few million years. The photons created in Rigel's core are born in a maelstrom of fusion reactions. They scatter through layers of plasma, moving at hundreds of kilometers per second. Some get pushed outward by radiation pressure, the sheer force of light itself. Rigel is so luminous that its radiation pressure nearly tears the star apart. Only gravity holds it together. In 1926, the British astrophysicist Arthur Eddington proposed that stars were powered by nuclear fusion, though the exact mechanisms weren't yet understood. He faced skepticism because the temperatures required seemed impossibly high. How could the core of a star be millions of degrees when the surface was only thousands? The answer lies in gravity. The more massive the star, the stronger gravity compresses the core, raising temperatures until fusion ignites. Eddington was right, though it took decades and advances in nuclear physics to confirm the details. Here's a strange thought. Every photon you've ever seen from the Sun is, in a sense, a ship of Theseus. The original gamma-ray photon created in the fusion reaction was absorbed and destroyed almost immediately. What emerged was a different photon, slightly less energetic. That photon was absorbed and another was emitted. This happened billions upon billions of times. By the time a photon finally reaches the Sun's surface, it's no longer a gamma-ray. It's been downgraded through countless absorptions and re-emissions into visible light infrared ultraviolet. The photon that reaches your eye is not the same one that was born in fusion. It's a descendant carrying the energy forward through generations of interactions. Scientists sometimes describe this journey as a drunkard's walk. Imagine someone staggering randomly, taking 1 step forward, 2 steps to the left, 1 step back, 3 steps to the right. On average, they're moving away from the starting point, but incredibly slowly. That's how photons escape a star. Statistically, they drift outward, but the path is so convoluted, so inefficient, that even traveling at the speed of light, they can take millennia to cross distances a rocket could cover in days. There's a concept in physics called optical depth. It's a measure of how opaque a material is to light. In the Sun's core, the optical depth is enormous. Light can't penetrate. It's like trying to see through a mountain made of milk. As you move outward from the core through the radiative zone, the density decreases, the temperature drops, and the optical depth slowly declines. Eventually, in the outer layers called the convective zone, the plasma is thin enough that photons can travel farther before being absorbed. Finally, at the photosphere, the visible surface, the plasma becomes transparent enough for photons to escape into space. When a photon finally breaks free from a star's surface, something remarkable happens. It stops interacting. In the vacuum of space, there's almost nothing to absorb it, no particles to scatter it. It simply flies straight and true at 299,792 kilometers per second, the cosmic speed limit. After tens or hundreds of thousands of years trapped in a stellar prison, bouncing endlessly, the photon is suddenly free. And it will remain free, traveling unimpeded until it hits something. A planet, a dust grain, an eye. But even in this freedom, the photon carries a memory. Its wavelength, its energy tells a story about the temperature of the surface it left behind. Hot stars emit more blue and ultraviolet light. Cool stars emit more red and infrared. By analyzing the spectrum of starlight, astronomers can determine a star's temperature composition age and even its motion through space. Every photon is a messenger carrying encoded information across the universe. There's a certain poetry to this struggle. Light, the fastest thing we know, spends most of its existence barely moving at all. Born in fire, trapped in density, scattered a billion times, and then only after an incomprehensible wait released to fly free. It's as if the universe requires patience even from its swiftest travelers. Even light must wait its turn. What mistakes do people make when thinking about starlight? The most common is assuming it's new. We see the sun and think its light is fresh created moments ago. But as we've seen, the energy in that light is ancient. Another mistake is thinking all stars are alike. A red dwarf and a blue supergiant are both stars, but their internal processes, their lifespans, their light production are vastly different. Comparing them is like comparing a candle to a forest fire. Both produce light, but the mechanisms and scales are incomparable. Perhaps the deepest lesson here is about time. We think of light as instantaneous because in our daily lives it seems to be. Flip a switch, the room brightens. But light's true nature is revealed only at cosmic scales. It's fast, yes, the fastest thing there is. But space is so vast and stellar, cores so dense that even light becomes slow. Even light must struggle. So the next time you feel sunlight on your skin, remember what it took for that light to reach you. The thermonuclear fury of fusion. The patient random wandering through a stellar maze. The final breakout into emptiness. That warmth you feel is the end of a journey that began before pyramids were built, before humans had language, before our ancestors walked upright. And it traveled all that way across time and space just to touch you for a fleeting second before disappearing forever. But escaping the star is only the beginning. Once free, the photon faces an entirely different challenge. The vast cold emptiness between stars. A void so wide that even traveling at light speed, crossing it, takes years, centuries, millennia. That's the next part of the journey, the loneliest part, where a single photon drifts through darkness, carrying its message toward an unknown destination, if any destination at all. The photon leaves the star's surface and everything changes. After millennia of chaos trapped and scattered, it finally moves the way it was meant to move. Forward. Only forward, at a speed so absolute, so fundamental to the fabric of reality that nothing in the universe can overtake it. 299,792 kilometers per second. That's the speed of light in a vacuum. It sounds like just a number until you try to picture what it means. In 1 second, light could circle the Earth 7.5 times. In 1 second, it travels farther than you could drive. In 3.5 days at highway speed, non-stop. And it does this every second forever, without slowing, without tiring, without wavering. But here's the strange part. For all its speed, light doesn't experience time. According to Einstein's theory of relativity, if you could ride along with a photon, time would stop. From the photon's perspective, its journey is instantaneous. It leaves the star and arrives at your eye in the same eternal moment. But for you, watching from outside, time passes normally. You see the delay. The photon is both infinitely fast and impossibly slow, depending on where you stand. Humans spent thousands of years trying to understand light's speed, and for most of history, they failed spectacularly. Aristotle believed light traveled instantaneously. It simply appeared wherever it needed to be, no journey required. This view dominated for centuries. Even the brilliant minds of the Renaissance struggled with the question. In 1638, Galileo attempted to measure the speed of light using lanterns on distant hilltops. He and an assistant would uncover their lanterns and try to detect the delay. They couldn't. The distance was too short, human reaction time too slow. Galileo concluded only that light was either instantaneous or extraordinarily fast. The breakthrough came in 1676, and it happened almost by accident. Danish astronomer Ole Romer was studying the moons of Jupiter, trying to create accurate tables for their orbits. He noticed something odd. When Earth was moving toward Jupiter, the moons appeared to orbit slightly faster than predicted. When Earth was moving away from Jupiter, they appeared slower. The moons themselves hadn't changed speed. The light carrying the image of their positions was taking longer or shorter to reach Earth depending on the distance. Romer calculated that light took about 22 minutes to cross the diameter of Earth's orbit around the Sun. His estimate for the speed of light was remarkably close to the modern value, off by only about 26%. For the first time in history, humans knew light had a finite speed. The universe had a speed limit. Over the next 2 centuries, measurements grew more precise. In 1728, James Bradley used stellar aberration, the apparent shift in star positions due to Earth's motion, to refine the estimate. In 1849, Hippolyte Fizeau used a rotating toothed wheel and a mirror 8 kilometers away to measure light's speed in a laboratory. He got within 1% of the true value. By 1862, Léon Foucault improved this using rotating mirrors. By the early 20th century, Albert Michelson had measured the speed of light to within a few parts per million using increasingly sophisticated methods. But it was Einstein in 1905 who revealed the deeper truth. The speed of light isn't just a speed, it's a cosmic constant, the same in all reference frames, regardless of how you're moving. This constancy leads to relativity's strangest predictions: time dilation, length contraction, the equivalence of mass and energy. The speed of light doesn't just describe how fast photons move. It defines the structure of space-time itself. So, when a photon leaves a star and enters the void, it's entering a realm governed by this constant. Space, contrary to what you might think, is not perfectly empty. It's a vacuum, yes, but not a perfect one. There are stray atoms, mostly hydrogen, about 1 per cubic centimeter, on average in interstellar space. There are magnetic fields threading through the galaxy. There's the cosmic microwave background, the faint afterglow of the Big Bang filling all of space with low-energy photons. There's dark matter, invisible and mysterious, exerting gravitational influence. And there's even something called the quantum vacuum, where particle-antiparticle pairs constantly pop into existence and annihilate within fractions of a second. Yet, for a photon traveling through this near emptiness, these obstacles are negligible. Unlike its journey through the star's dense core, where it collided constantly, space offers almost no resistance. The photon flies in a straight line, or as straight as space-time allows, because space-time isn't flat. It's curved by mass and energy. Every star, every planet, every galaxy bends the fabric of space around it. A photon traveling through curved space-time will follow the curve not because anything is pushing it, but because the straight line itself is curved. Think about this carefully. When you throw a ball, it follows a curved arc because gravity pulls it down. But the ball is moving through flat space and being accelerated by a force. A photon doesn't experience it that way. From the photon's perspective, it's always moving straight ahead. But the space it's moving through is warped. The shortest path between 2 points in curved space-time is called a geodesic, and that's the path light follows. Einstein called this the equivalence principle, the idea that gravity isn't a force pulling on objects, but rather a consequence of space-time curvature. This has profound implications. A photon leaving a massive star will have its path bent by the star's gravity as it departs. If the star is extremely dense, like a neutron star, the bending can be severe. Some photons that would normally escape get pulled back, captured by the curvature. If the star collapses into a black hole, space-time curves so sharply that beyond a certain boundary, the event horizon, not even light, can escape. The photons are trapped forever, falling endlessly toward the singularity. For a photon, a black hole is the ultimate prison, worse than the densest stellar core. But most stars aren't black holes. Most photons do escape, and once free, they travel vast distances without interruption. Yet, even empty space isn't entirely transparent. Over very long distances, some photons do encounter obstacles. A photon might hit a stray hydrogen atom, getting absorbed and re-emitted in a random direction. This is rare, but over millions of light years, it becomes statistically significant. Astronomers studying distant galaxies have to account for this scattering, which can blur images and reduce the light we receive. There's also dust. Interstellar dust grains, tiny particles of carbon silicon, and other elements float through space. They're remnants of dead stars scattered by supernovae and stellar winds. These grains are incredibly small, often just a few hundred nanometers across, but they're numerous enough to block or scatter light over great distances. This is why the center of our galaxy, though incredibly bright with billions of stars, appears dim and obscured from Earth. Dust clouds lie between us and the galactic core, absorbing and scattering the light. Infrared light with longer wavelengths can pass through dust more easily than visible light, which is why infrared telescopes can peer into regions invisible to optical telescopes. One of the most common mistakes people make is thinking light always travels at the same speed everywhere. It doesn't. The speed of light, 269,792 kilometers per second, is its speed in a vacuum. When light enters a medium like water glass or even air, it slows down. This slowing happens because photons interact with the atoms in the material getting absorbed and re-emitted, which introduces delays. In water, light travels at about 225,000 kilometers per second, roughly 75% of its vacuum speed. In diamond, it's even slower, about 124,000 kilometers per second. This change in speed is why light bends when it enters a new medium, a phenomenon called refraction. But in the vacuum of space, there's no medium to slow it down. The photon moves at maximum speed, c, the universal constant. This constancy is so fundamental that scientists now define the meter based on the speed of light. 1 meter is the distance light travels in 1,269,792 458th of a second. The speed of light doesn't just measure space, it defines it. Now imagine you're the photon. You've escaped the star. You're flying through space at 2,99792 kilometers per second. How long until you encounter something? If you're heading directly toward a nearby star, you might reach it in a few years. Alpha Centauri. The closest star system to our Sun is about 4.37 light-years away. A photon leaving the Sun toward Alpha Centauri would arrive in just over 4 years. But the odds of any given photon heading directly toward another star are astronomically small. Most photons fly off into the void between stars, and space is shockingly empty. The average distance between stars in our galaxy is about 5 light-years. In some regions, it's much more. A photon could travel for tens, hundreds, even thousands of years without hitting anything significant. Some photons never encounter anything at all. They fly forever, crossing galaxies, slipping between galaxy clusters, journeying through the expanding universe until the cosmos itself grows too cold and diffuse to support any structure. These photons become cosmic wanderers, eternal travelers with no destination. In a very real sense, most light in the universe is lost. It flies into darkness and never returns. But some photons get lucky. They find a planet. They find an atmosphere, they find an eye. And when they do, when a photon born in a star millions of years ago finally collides with a molecule in your retina, something extraordinary happens. Information transfers. Energy transfers. You see, for a fraction of a second, you and that photon, you and that distant star are connected. The photon's journey ends and your experience of it begins. There's something humbling in knowing that light doesn't travel instantaneously. For a long time, humans assumed it did. The idea that sight could be delayed, That we might be seeing the past rather than the present was almost unthinkable. But once we understood light's finite speed, we had to confront an uncomfortable truth. There is no universal now. Every point in space has its own timeline. When you look at the moon, you see it as it was 3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at Proxima Centauri, you see it as it was 4.2 years ago. And when you look at the Andromeda Galaxy, you see it as it was 2.5 million years ago, long before humans existed. This means the universe you observe is a patchwork of different moments, all stitched together by the speed of light. You're not looking at a single present. You're looking at a cascade of pasts, each one layered at a different distance, a different depth of time. The night sky is a museum, and every exhibit is from a different era. Einstein once described this beautifully. He said that for those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. Time as we experience it is not the same as time in the universe. Our experience of now is local, tied to our position in space and our motion through it. But the universe doesn't have a now. It has light cones, causal structures, regions of space-time that can influence each other, only if light has had time to travel between them. So, when a photon escapes a star and begins its journey through the void, it's not just traveling through space, it's traveling through time. It's carrying information from one moment to another, from one place to another, linking past and present across the emptiness. And the longer the journey, the more profound the connection. A photon from a star a billion light years away is a messenger from an ancient universe, a cosmos, vastly different from the one we inhabit now. But the photon doesn't care about any of this. It has no awareness, no purpose, no intention. It simply moves. That's all it knows how to do. And in that simplicity, there's a strange kind of grace. Light doesn't question. It doesn't hesitate. It just is, and it goes, and eventually maybe it arrives. Yet the journey isn't always smooth. Even in the vastness of space, things happen. Photons encounter gravitational fields, magnetic storms expanding space-time itself. These forces don't stop the photon, but they change it, stretch it, bend it. That's what we're turning toward. Now, the ways the universe reshapes light as it travels, altering its journey in subtle and profound ways, leaving clues we can read if we know how to look. Space is not just empty. It's profoundly, achingly alone. A photon traveling between stars moves through a silence so complete, a void so vast, that the word distance stops meaning what it used to mean. Out here, measurements break down. Numbers become abstract. And time, already strange, becomes something else entirely. Consider this: if you could shrink the sun to the size of a golf ball, the nearest star, Proxima Centauri, would be another golf ball about 1/300 kilometers away. That's the distance from New York to Miami. And between those two golf balls, there would be almost nothing. A few grains of sand representing planets, wisps of gas too thin to see, darkness, silence, cold, approaching absolute zero. This is the cosmic desert, and every photon that travels between stars must cross it alone. Proxima Centauri is 4.24 light-years away from us. That means the light we see from it tonight left that star in late 2021. It traveled through the void for over 4 years, covering a distance of about 40 trillion kilometers, roughly 25 trillion miles. To put that in perspective, if you drove a car at highway speed non-stop, it would take you about 48 million years to cover the same distance. The fastest spacecraft humans have ever built, the Parker Solar Probe, traveling at its peak speed of 163 kilometers per second, would still need over 7,700 years to reach Proxima Centauri. But the photon made the journey in just 4.24 years, and from its own reference frame, no time passed at all. This is the loneliness of light. It moves so fast that time stops for it, yet from our perspective, it crawls across distances so enormous they defy comprehension. A photon doesn't feel loneliness, of course. It doesn't feel anything. but if it could imagine what it would witness. Centuries of travel through absolute nothingness. No landmarks, no rest stops, no other travelers. Just the endless unchanging black, punctuated occasionally by the faint glow of distant stars too far away to matter. Most stars in our galaxy are separated by roughly 5 light years. Some are closer, some much farther. In the sparse regions between the spiral arm stars can be dozens of light years apart. A photon leaving one of these isolated stars might travel for 50, 100, even 200 years before encountering anything significant. During that time, entire human generations would be born live and die on Earth. Civilizations could rise and fall, technologies could be invented and forgotten, and the photon would just keep going indifferent to it, all carrying its tiny packet of energy through the void. But what exactly is this void? We call it empty space, but that's not quite accurate. Interstellar space contains about 1 hydrogen atom per cubic centimeter on average. That sounds like almost nothing, and it is compared to Earth's atmosphere, which contains about 10 to the 19th power molecules per cubic centimeter. But over vast distances, even 1 atom per cubic centimeter adds up. If you travel a light year through interstellar space, you'll pass through about 30 trillion hydrogen atoms. Most photons pass right by these atoms without interacting, but some don't. Some collide, get absorbed, and re-emitted in a different direction. Over millions of light years, this scattering becomes noticeable. There's also interstellar dust, those tiny grains we mentioned earlier. They're sparse, perhaps 1 grain per 10 million cubic meters, but they have a disproportionate effect on light. Dust grains are roughly the same size as the wavelength of visible light, which makes them incredibly efficient at scattering it. Blue light, with its shorter wavelength, scatters more easily than red light. This is why distant stars often appear redder than they actually are. The blue light gets scattered away, and only the red makes it through. Astronomers call this interstellar reddening, and they have to correct for it when studying distant objects. Then there's the interstellar magnetic field. Our galaxy is threaded with magnetic fields weak by Earth standards but significant over cosmic scales. These fields don't affect photons directly because photons have no electric charge, but they do affect charged particles like electrons and protons, which in turn affect the distribution of matter in space. Magnetic fields help shape nebulae, guide cosmic rays, and influence star formation. A photon traveling through these regions might not feel the magnetic field itself, but it navigates a landscape sculpted by magnetism. And then there's dark matter. We can't see it, we can't touch it, and we don't know what it's made of, but we know it's there because of its gravitational effects. Dark matter makes up about 85% of the matter in the universe. It doesn't emit light, doesn't absorb light, doesn't scatter light. Photons pass right through it as if it doesn't exist. Yet dark matter's gravity shapes the paths those photons take, bending space-time in ways we can measure. When astronomers map the distribution of dark matter in galaxy clusters, they do it by observing how light from background galaxies is bent and distorted. The photons themselves carry no direct information about dark matter, but their paths reveal its presence. Have you ever wondered what it would look like to travel at light speed through space? Science fiction often shows stars streaking past like lines, a visual effect called star trails. But that's not accurate. If you were somehow riding a photon, you wouldn't see anything streak by, because from your perspective, the journey would be instantaneous. You'd leave the star and arrive at your destination in the same moment. There would be no experience of travel, no sense of motion, no passage of time. Relativity forbids it. Only outside observers see the photon's journey taking time. But let's imagine you're traveling just below light speed, close enough to experience extreme time dilation, but slow enough to still perceive the universe. What would you see? The stars ahead would appear blue-shifted, their light compressed into higher frequencies. The stars behind would be red-shifted, stretched into longer wavelengths. And the stars to your sides would seem to converge toward the front, a phenomenon called relativistic beaming. The faster you go, the more pronounced these effects become. At 99.9% of light speed, the entire sky would seem to compress into a bright disk ahead of you, with everything else fading into darkness. Photons don't experience this because they're always at light speed, always in that singular state where time and space collapse into a single point. But for anything traveling slower, the universe becomes increasingly strange the faster you move. This is why interstellar travel, even if we could achieve speeds close to light, would be profoundly disorienting. The cosmos you'd see wouldn't resemble the cosmos we observe from Earth. Let's talk numbers for a moment. A light year is 9.46 trillion kilometers. The nearest large galaxy to our own Andromeda is about 2.5 million light years away. That's 23.65 sextillion kilometers a number, so large it's essentially meaningless to human intuition. Light from Andromeda that reaches your eye tonight began its journey 2.5 million years ago during the Paleolithic era, when our ancestors were just learning to make stone tools. Every photon from Andromeda is a time traveler carrying an image of that galaxy from an age unimaginably distant. And Andromeda is close, cosmically speaking. The observable universe extends about 46.5 billion light years in every direction. That's not a typo. Even though the universe is only 13.8 billion years old, expansion has stretched space itself, carrying distant galaxies farther away than light has had time to travel. The most distant light we can see, the cosmic microwave background, comes from regions now about 46 billion light years away. Those photons have been traveling for 13.8 billion years, crossing an expanding universe, enduring a loneliness incomprehensible even by cosmic standards. Most photons never complete such journeys. They get absorbed by dust, scattered by gas, or simply fly off into regions of space we'll never see. The universe is expanding, and as it expands, distant galaxies are receding faster and faster. Beyond a certain distance called the cosmic event horizon, galaxies are receding faster than light can travel. Photons leaving those galaxies will never reach us, no matter how long they travel. They're trapped in an expanding bubble of space-time, forever out of reach. In a sense, these photons are even lonelier than the ones that do arrive because their journey has no possible end. There's a concept in cosmology called the cosmological horizon problem. It's the observation that regions of the universe too far apart to have ever exchanged light are nonetheless remarkably similar in temperature and density. How did they become so uniform if light has never had time to travel between them? The leading explanation is cosmic inflation, a period in the universe's first fraction of a second, when space expanded faster than light. During inflation, regions that were once close enough to interact were blown apart, stretched to opposite sides of the observable universe. The light connecting them was literally pulled apart by expanding space. These photons still exist somewhere, but they're so redshifted, so stretched by expansion, that they're no longer detectable as light. They've become radio waves, microwaves, part of the cosmic background hum. One of the most common misconceptions about space travel is thinking of it like ocean travel. You plot a course, you sail, you arrive. But space isn't like the ocean. The ocean has currents, winds, landmarks. Space has none of that. Worse, space is expanding. If you aim for a distant galaxy and travel toward it at any speed slower than light, the galaxy is receding as you approach. Depending on how far away it is, you might never catch it, no matter how long you travel. The universe is running away from itself, and light is the only thing fast enough to keep up barely. This brings us to one of the strangest truths about cosmic distances. When we say a galaxy is a billion light years away, we don't mean the light took a billion years to reach us. Well, we do. But the galaxy isn't there anymore. It's farther now, because space has been expanding the entire time the light was traveling. The light we see shows us where the galaxy was a billion years ago, but where it is now might be 5 billion light years away or more. We're always seeing the past, and the past is always receding. Think about the photons crossing these distances. They don't know their destination. They don't know if they'll ever arrive anywhere. They just go. Some will hit a dust grain after 1,000 years. Some will travel for 1,000,000 years and land on a distant planet's surface. Some will travel for billions of years and arrive at a time when the universe is cold, dark, and devoid of stars. And some, a very lucky few, will travel across the cosmos and land on a retina where they'll be absorbed by a molecule called rhodopsin, triggering a cascade of chemical reactions that result in a single thought: I see a star. The loneliness of these journeys is staggering. Each photon is a solitary traveler in an unimaginably vast desert. No companions, no destination guaranteed, no assurance that the journey will mean anything. And yet they go billions upon billions of them, pouring out from every star, filling the universe with light that mostly goes unseen. But even in this loneliness, there's connection. Every photon that does arrive, every bit of starlight that reaches an eye or a telescope bridges the gulf. For a moment, the isolation ends. The photon completes its journey and information flows. We learn something about the star, the galaxy, the universe. The loneliness serves a purpose, even if the photon doesn't know it. So, the next time you see starlight, remember the journey it took. The years, the centuries, the millennia of solitary travel through an empty, expanding cosmos. That light didn't have to reach you. Statistically, it almost certainly shouldn't have, but it did. Against all odds across all that distance, it found you. And now, because of that meeting, you know something you didn't before. You've touched a part of the universe you'll never physically reach connected to it, through the fragile thread of a single photon's unlikely journey. Yet the journey isn't over, and the loneliness isn't the only challenge light faces. As it travels, the universe itself acts upon it, stretching it, bending it, changing it in ways both subtle and profound. These transformations leave signatures, clues we can decode. That's where we turn next to the forces that shape light's path, the invisible hands that guide every photon toward its uncertain fate. Light travels in straight lines. At least that's what we're taught. Draw a laser across a room and the beam goes perfectly straight. Shine a flashlight and the light spreads in straight rays. But this is only true in flat, empty space. And the universe is neither flat nor empty. Out in the cosmos, light bends, warps, and stretches in ways that reveal the hidden architecture of reality itself. Imagine space-time not as emptiness, but as a fabric, a flexible sheet that can be pulled, curved, and distorted by mass and energy. Every star, every planet, every galaxy creates a dent in this fabric, and when light passes through these dents, it follows the curves. It's still traveling in a straight line from its own perspective, but the straight line itself is bent. This is gravity not as a force pulling objects together, but as the geometry of space-time itself. Einstein predicted this in 1915 with his general theory of relativity, but it took 4 years to prove it. In 1919, during a total solar eclipse, British astronomer Arthur Eddington led expeditions to photograph stars near the sun's edge. Normally, you can't see stars near the sun because the sun's brightness overwhelms them. But during a total eclipse, the moon blocks the sun's light, revealing the stars behind it. Eddington measured the positions of these stars and compared them to their positions when the sun wasn't nearby. The stars had shifted just as Einstein predicted. The sun's gravity had bent the starlight passing near it, making the stars appear to be in slightly different positions. The amount of bending matched Einstein's equations almost perfectly. It was one of the most dramatic confirmations of a scientific theory in history, and it made Einstein a global celebrity overnight. This bending of light by gravity is called gravitational lensing, and it happens everywhere in the universe. When light from a distant galaxy passes near a massive object like another galaxy or a cluster of galaxies, the light's path curves. From our perspective on Earth, this can create multiple images of the same galaxy, distorted arcs of light, or even complete rings. Astronomers call these Einstein rings, and they're hauntingly beautiful, perfect circles of light wrapped around the lensing mass. One of the most famous examples is the Einstein cross discovered in 1985. It's a quasar, an extremely bright and distant object, powered by a supermassive black hole located about 8 billion light-years away. Between us and the quasar sits a galaxy about 400 million light-years away. The galaxy's gravity bends the quasar's light, splitting it into 4 distinct images arranged around the galaxy's center. When you look at the Einstein cross through a telescope, you're seeing the same quasar 4 times each image, showing the quasar at a slightly different moment in time, because each light path took a slightly different route around the lensing galaxy. Think about that. 4 different paths, 4 different journeys, all arriving at your eye simultaneously. The photons in each image left the quasar at nearly the same instant, but they traveled different paths through curved space-time, and so they arrive at different times. The time delay between images can range from hours to years depending on the geometry. Astronomers use these time delays to measure cosmic distances and study the expansion of the universe. Gravitational lensing isn't just a curiosity, it's a tool. Astronomers use it to study dark matter, that invisible substance that makes up most of the matter in the universe. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with light directly. But it does have mass and mass-curved space-time. By studying how light from distant galaxies is bent and distorted as it passes through galaxy clusters, astronomers can map the distribution of dark matter. They have found that dark matter surrounds galaxies in vast halos far larger than the visible galaxies themselves. Without gravitational lensing, we'd have no way to see this invisible scaffolding of the cosmos. But gravity isn't the only force shaping light's journey. There's also the expansion of the universe itself. When a photon leaves a distant galaxy and begins traveling toward us, space itself is expanding. As space stretches, the photon's wavelength stretches with it. Light that was emitted as blue might arrive as red. Light that was ultraviolet might arrive as visible. Light that was visible might arrive as infrared. This stretching of wavelength is called cosmological redshift, and it's one of the most important clues we have about the universe's history and structure. The farther away a galaxy is, the faster it's receding from us due to cosmic expansion, and the more its light is redshifted. In 1929, Edwin Hubble discovered this relationship while studying the spectra of distant galaxies. He found that nearly all galaxies showed redshifted spectral lines, meaning they were moving away from us. Moreover, the farther away a galaxy was, the greater its redshift. This was the first concrete evidence that the universe is expanding. Before Hubble, many scientists believed the universe was static and eternal. Hubble's observations shattered that view and gave birth to modern cosmology. Redshift is measured using a value called Z. A redshift of Z equals 1 means the wavelength of light has doubled during its journey. A redshift of Z equals 2 means it has tripled. The most distant galaxies we've observed have redshifts around ZB equals 10 or higher, meaning their light has been stretched to more than 11 times its original wavelength. These galaxies are so far away that the light we see left them when the universe was less than 500 million years old, just a fraction of its current age of 13.8 billion years. But redshift doesn't just tell us about distance, it tells us about time. When we look at a galaxy with a redshift of Z equals 6, we're seeing it as it was when the universe was only about 900 million years old. We're looking back across 12.9 billion years of cosmic history. The photons reaching our telescopes have traveled through an expanding universe for most of the time that universe has existed. They have been stretched, pulled, transformed by the very fabric of space itself. And here's something even stranger. Because space is expanding, the speed at which distant galaxies are receding from us can exceed the speed of light. Weight doesn't, relativity say nothing, can travel faster than light. Yes, but that applies to objects moving through space. Space itself can expand as fast as it wants. In fact, galaxies beyond a certain distance, about 14.5 billion light-years away, in what's called the Hubble sphere, are receding faster than light. This doesn't mean they're breaking the speed limit. It means the space between us and them is stretching faster than light can cross it. This has profound implications. It means there are galaxies whose light will never reach us, no matter how long we wait. The photons they emit are swimming upstream in an expanding river of space-time, and the river is flowing too fast. These galaxies are beyond what's called the cosmic event horizon, forever out of reach. The observable universe is not the entire universe. It's just the part of the universe from which light has had time to reach us. Beyond that boundary, there could be infinite galaxies, infinite stars, infinite worlds, all invisible to us forever. Now, let's talk about blue shift. It's the opposite of redshift. When an object is moving toward us, its light gets compressed, shifting toward shorter wavelengths. Blue light becomes ultraviolet green, becomes blue-red, becomes green. Blue shift is rarer than redshift on cosmic scales because most of the universe is expanding away from us. But it does happen. The Andromeda Galaxy, for instance, is blue shifted. It's moving toward us at about 110 kilometers per second. In about 4 billion years, Andromeda will collide with our Milky Way, and the two galaxies will merge. The photons we see from Andromeda tonight are slightly bluer than they were when they left, compressed by the galaxy's approach. Gravitational fields can also cause redshift and blue shift, separate from motion. When light climbs out of a deep gravitational well, such as escaping from near a black hole or a neutron star, it loses energy. Its wavelength stretches, shifting toward the red. This is called gravitational redshift. Einstein predicted it, and it's been measured precisely in laboratories on Earth using atomic clocks at different altitudes. A clock on the ground runs slightly slower than a clock on a mountaintop because the ground clock is deeper in Earth's gravitational field. The same effect applies to light. Photons climbing out of Earth's gravity lose a tiny amount of energy, shifting very slightly toward the red. Near a black hole's event horizon, gravitational redshift becomes extreme. As light tries to escape from closer and closer to the horizon, it becomes more and more redshifted. At the horizon itself, the redshift becomes infinite. The light's wavelength stretches to infinity, its frequency drops to zero, and it effectively disappears. This is part of why black holes are black. Light emitted from the event horizon is infinitely redshifted, rendering it invisible. There's a beautiful symmetry here. The universe shapes light, and light reveals the universe. Every bend, every stretch, every shift in wavelength carries information. By studying how light has been altered during its journey, astronomers can reconstruct the path it took, the masses it passed, the expansion it endured. Light is a messenger, but it's also a record carrying within it the story of its travels. One mistake people often make is thinking redshift and blue shift are like the Doppler effect for sound. It's similar, but not identical. The Doppler effect for sound happens because the source is moving through a medium, air. But light doesn't need a medium. Space itself can be expanding or contracting, and that changes the wavelength in ways the Doppler effect alone can't explain. Cosmological redshift isn't caused by galaxies moving through space. It's caused by space itself stretching between us and those galaxies. The distinction is subtle but crucial. Another common misconception is that gravitational lensing magnifies distant objects like a glass lens. It can, but it's not a simple magnification. Gravitational lensing distorts. It stretches images into arcs, splits them into multiple copies, and brightens some parts while dimming others. The effect depends on the exact alignment of the source, the lens, and the observer. Sometimes lensing makes a galaxy appear brighter and more detailed, allowing us to see objects we otherwise couldn't. Other times it creates bizarre funhouse mirror distortions that are difficult to interpret. Have you ever considered what this means for our view of the universe? Every image we have of the distant cosmos has been shaped by gravity and expansion. The galaxies we see aren't where they appear to be. Their light has been bent around intervening masses stretched by billions of years of cosmic expansion. We're not seeing the universe as it is. We're seeing a distorted, time-delayed, gravity-warped version of what it was. It's like looking at the world through a funhouse mirror, except the mirror is space-time itself. And yet, from this distorted view, we've learned extraordinary things. We've mapped the distribution of dark matter. We've measured the rate of cosmic expansion. We've discovered that the expansion is accelerating, driven by something called dark energy, a mysterious force that makes up about 68% of the universe's total energy. We know this because of how light behaves, how it bends, how it stretches, how it changes during its journey. Light may be shaped by the universe, but it also shapes our understanding of the universe in return. So, the photon continues its journey, bent by gravity, stretched by expansion, carrying within it a history written in wavelength and direction. But eventually, for the luckiest photons, the journey nears its end. Ahead lies a planet, an atmosphere, and perhaps an eye waiting in the darkness. That final approach, that last collision, is where the ancient and the immediate meet, where distance becomes sight, where the photon's long loneliness finally briefly ends. Every star you see in the night sky is a ghost, not in the supernatural sense, but in a literal physical way. The light reaching your eyes tonight didn't leave those stars tonight. It left years ago, centuries ago, sometimes millions of years ago. You're not seeing the stars as they are. You're seeing them as they were. And some of them, the stars that burn brightest in your childhood sky, might not exist anymore at all. Let's start close to home. Sirius. The brightest star in the night sky sits in the constellation Canis Major, the Great Dog. On a clear winter night, you can't miss it. It blazes white-blue, sometimes seeming to twinkle with colors because of atmospheric turbulence. Sirius is 8.6 light-years away. That means when you look at Sirius tonight, you're seeing light that left that star in early 2017. If Sirius exploded yesterday, you wouldn't know for another 8.6 years. The explosion's light would still be traveling toward you, crossing the void at 299,792 kilometers per second, carrying news of an event you're blissfully unaware of. Now, consider Vega, the bright blue-white star in the constellation Lyra. Vega is about 25 light-years away. The light you see from Vega tonight departed in the year 2001, around the time of the September 11th attacks, the launch of Wikipedia, and the release of the first iPod. That photon has been traveling through space for your entire adult life, or your entire childhood, depending on your age. It left Vega before smartphones existed, before social media transformed communication, before many of the technologies you use daily were even invented. But let's go farther. Betelgeuse, that red supergiant marking Orion's shoulder, is approximately 5 light-years away. The light you see from Betelgeuse tonight left that star around the year 1382. Think about what was happening on Earth then. The Ming Dynasty was rising in China. The 100 Years' War was raging in Europe. The Black Death had just finished devastating populations across 3 continents. Chaucer was writing the Canterbury Tales. The Renaissance hadn't begun. America hadn't been discovered by Europeans. Gutenberg hadn't invented the printing press. And somewhere out in space, a photon left Betelgeuse and began a journey that would take more than 6 centuries. Here's the haunting part. Betelgeuse is dying. It's a red supergiant in the final stages of stellar evolution. Its core is running out of fuel. At some point, possibly soon, in cosmic terms, the core will collapse and the star will explode in a supernova so bright it might briefly be visible during the day from Earth. When will this happen? We don't know. It could be tomorrow. It could be 100,000 years from now. But here's the thing, it might have already happened. If Betelgeuse exploded 500 years ago, the light from that explosion wouldn't reach us for another 142 years. The star could be gone, obliterated, scattered into space, and we'd still see it shining in Orion's shoulder every winter night, oblivious to its death. Astronomers estimate that if Betelgeuse does go supernova, it will be as bright as the full moon casting shadows at night, visible even in broad daylight. It would be the astronomical event of a lifetime, a once-in-a-civilization spectacle. But we're not seeing Betelgeuse now. We're seeing its ghost, the light echo of what it was doing 6.5 centuries ago. The star's present moment is unknowable to us. We're trapped in its past. Let's go even farther. Deneb, the tail star in the constellation Cygnus the Swan, is one of the most distant stars visible to the naked eye. Its distance is somewhat uncertain, but current estimates place it around 2,600 light-years away. The light you see from Deneb tonight left that star around 600 BCE during the time of the ancient Greek philosophers, the founding of the Roman Republic, and the life of Buddha. That photon has been traveling through space longer than any human civilization has existed in its current form. It passed through the void while empires rose and fell, while languages were born and died, while entire genealogies of human culture unfolded and vanished. And Deneb is still relatively close, cosmically speaking. The Andromeda Galaxy, visible as a faint smudge to the naked eye under dark skies, is about 2.5 million light-years away. The light from Andromeda that's entering your eye right now began its journey 2.5 million years ago during the Paleolithic era. Our genus Homo had only recently emerged. Homo habilis, one of our early ancestors, was making crude stone tools in Africa. No humans had left Africa yet. No one had discovered fire. Language, art, agriculture, civilization, all of it lay millions of years in the future. And while our ancestors were just learning to be human, photons were leaving the Andromeda Galaxy, beginning an incomprehensibly long journey across intergalactic space. Think about what those photons witnessed in a metaphorical sense. They left Andromeda when Earth was in an ice age. They traveled through the void, while our species evolved, migrated, spread across the planet. They passed through space while we invented tools, language, culture, writing, mathematics, science. They crossed the cosmic desert while we built cities, fought wars, created art, discovered the very laws of physics that govern their motion. And then tonight, after 2.5 million years of travel, one of those photons happened to land on your retina. For a tiny fraction of a second, you and that ancient photon, you and that distant galaxy are connected. But Andromeda is rushing toward us. It's one of the few large galaxies in our local group that's blue-shifted instead of red-shifted. In about 4 billion years, Andromeda and the Milky Way will collide. Not a violent crash, but a slow merging as the two galaxies pass through each other, their stars rearranging under mutual gravitational influence. The night sky will transform. Stars will fill the view. The collision will trigger waves of new star formation as gas clouds compress and ignite. Eventually, the two galaxies will settle into a new structure, a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. But that's billions of years away. The light you're seeing from Andromeda tonight shows you that galaxy as it was long before humans existed, long before Earth had developed complex life, perhaps even before Earth's continents had taken their current shapes. Let's talk about the stars of the Big Dipper, one of the most recognizable patterns in the northern sky. It's not actually a constellation, it's an asterism, a pattern within the larger constellation Ursa Major. The 7 main stars of the Big Dipper are at vastly different distances. Alkaid, the star at the end of the handle, is about 101 light-years away. Dubhe, one of the pointer stars, is about 123 light-years away. Megrez, the faintest of the 7, is roughly 58 light-years away. When you look at the Big Dipper, you're seeing stars from different eras. The light from Megrez left in the 1960s. The light from Alkaid left during World War I. They're not even close to each other in space. They just happen to line up from our perspective, creating a pattern that's only meaningful from Earth. In 50,000 years, the stars will have moved enough in their individual orbits around the galaxy that the Big Dipper will look completely different. The pattern is temporary, a snapshot of cosmic motion, frozen by the limitations of human perception. Now, consider the stars you can't see with your naked eye. The Hubble Space Telescope has photographed galaxies so distant, their light has been traveling for over 13 billion years. These galaxies existed when the universe was less than 700 million years old, just 5% of its current age. The stars in those galaxies formed from primordial gas, mostly hydrogen and helium, with almost no heavy elements. They were massive, short-lived burning furiously and dying young in supernova explosions that scattered the first heavy elements into space. Those elements would later form new stars, planets, and eventually life. The light from those first galaxies shows us the universe in its infancy, a time when structure was just beginning to form, when the first stars were lighting up the cosmic dark ages. But here's a strange thought. Most of those stars are dead now. They died billions of years ago. The galaxies still exist, but they've changed dramatically. They've merged with other galaxies, formed new stars, evolved in ways we can't see. What we're observing is history frozen in light, traveling across an expanding universe to reach our telescopes. We're archaeologists of light studying the fossilized past of the cosmos. And there's a deeper strangeness still. Because of cosmic expansion, the most distant galaxies we can see are receding faster than light. Not moving through space faster than light, which is impossible, but being carried away by the expansion of space itself. This means the light we're seeing from them today is the last light that will ever reach us. Future photons leaving those galaxies will be swimming upstream in an expanding river of space-time, unable to make progress toward us. The universe is slowly closing off, becoming less and less observable as expansion accelerates. We're living in a relatively young universe, a time when we can still see much of cosmic history. Trillions of years from now, if any civilizations exist, they'll see a much smaller, much darker universe with most of the galaxies we observe, now having receded beyond the cosmic event horizon, invisible forever. This raises a philosophical question. If we're seeing the past, not the present, is there even such a thing as a universal present? The answer from relativity is no. There's no universal now. Every point in space has its own timeline, and those timelines don't synchronize across cosmic distances. When you look at a star 10 light years away, you're seeing it as it was 10 years ago. But from that star's perspective, looking at Earth, they'd see us as we were 10 years ago. There's no shared moment, no common present tense. The universe is a patchwork of different times, stitched together by the speed of light. One of the most common mistakes people make is assuming the night sky shows them the current state of the universe. It doesn't. It shows them a layered history with nearby objects appearing almost as they are now, and distant objects appearing as they were long ago. Every depth of view is a different moment in time. The farther you look, the farther back you see. Cosmology is the only science where looking farther away literally means looking farther into the past. Geologists study ancient rocks. Paleontologists study ancient fossils. But astronomers study ancient light, direct evidence from billions of years ago. Another misconception is that all stars live forever, or at least for incomprehensibly long times. Some do. Red dwarf stars can live for trillions of years. But massive stars, the bright blue giants, live only a few million years before exploding as supernovae. Betelgeuse, despite being visible for all of recorded history, has only existed for about 8 to 10 million years. In cosmic terms, that's a blink, and it's already nearing the end. The brightest stars in our sky are often the youngest and shortest-lived, burning through their fuel at prodigious rates. They dominate our view not because they're common, but because they're extraordinarily luminous. Most stars are dim red dwarfs, far too faint to see without a telescope. So, when you look up at the night sky, what you're really seeing is a temporal mosaic. Sirius from 2017, Vega from 2001, Betelgeuse from 1382, Deneb from 600 BCE, Andromeda from 2.5 million years ago, and the cosmic microwave background visible only with radio telescopes from 13.8 billion years ago, the oldest light we can ever see. Every photon carries a timestamp encoded in the distance it traveled. The universe is a time machine, and the night sky is the interface. There's something both melancholic and beautiful about this. The stars we cherish might already be gone. The constellations our ancestors used to navigate, to tell stories, to mark the seasons, are made of ghosts. And yet those ghosts are all we have. We can't see the present of distant stars. We can only see their past. But in seeing their past, we learn about the universe's past and by extension our own origins. Every atom in your body was forged in a star that died before our solar system formed. You are made of stellar ashes, and the light you see is the echo of that ancient creation still reverberating through space. So, the next time you see Betelgeuse glowing red in Orion's shoulder, remember that light is older than the United States, older than the scientific revolution, older than the Renaissance. And it traveled across 642 years of empty space just to land on your eye tonight. It's a messenger from the past, and its message is simple: I existed, I burned, I sent this light to you, and whether I still exist now, you will not know for centuries more. But eventually, after crossing all that time and distance, light reaches a final barrier. Not emptiness, not gravity, not expansion, but something more immediate: an atmosphere, a planet, an eye. That last collision, that final transformation, is where we go now, to the place where ancient starlight becomes sight. A photon crosses light years of emptiness, survives. The warping of space-time carries its message through cosmic expansion and finally approaches a blue planet. After centuries or millennia of solitary travel, it encounters something it hasn't faced since leaving its star matter. Lots of it. And this final barrier, Earth's atmosphere, will transform the photon one last time before it reaches your eye. The atmosphere is a thin shell of gas, mostly nitrogen and oxygen, wrapped around our planet. It's only about 100 kilometers thick, roughly the distance you might drive in an hour, yet it's thick enough to completely alter how we see the universe. Without it, the sky would be black even during the day stars visible alongside the sun. With it, the sky is blue stars invisible in daylight, and the night sky shimmers and dances with atmospheric effects. When a photon from a distant star first enters Earth's atmosphere, it encounters molecules of nitrogen and oxygen. These molecules are tiny, far smaller than the wavelength of visible light, and when light hits them, something interesting happens. The light scatters. This scattering is called Rayleigh scattering, named after the British physicist Lord Rayleigh, who mathematically described it in 1871. Rayleigh scattering is wavelength dependent. Shorter wavelengths like blue and violet light scatter far more efficiently than longer wavelengths like red and orange. In fact, blue light scatters about 10 times more than red light. This is why the daytime sky is blue. Sunlight enters the atmosphere as white light, a mixture of all visible wavelengths. As it passes through the air, the blue and violet wavelengths scatter in all directions, filling the sky with blue light. The red and orange wavelengths pass through more directly, which is why the sun itself appears yellowish white rather than pure white. We don't see a violet sky, even though violet scatters even more than blue, because our eyes are less sensitive to violet, and because the sun emits less violet light to begin with. At sunset and sunrise, the story changes. When the sun is near the horizon, its light has to pass through much more atmosphere to reach you, sometimes 30 times more than when it's directly overhead. All that extra air scatters away nearly all the blue light, leaving mostly reds, oranges, and yellows. This is why sunsets are red. The atmosphere is filtering the sunlight, removing the shorter wavelengths and letting the longer ones through. Volcanic eruptions and wildfires can intensify this effect by adding particles to the upper atmosphere, creating spectacularly vivid sunsets that can last for months or even years after the event. But Rayleigh scattering isn't the only thing happening in the atmosphere. There's also absorption. Water vapor, carbon dioxide, and ozone absorb specific wavelengths of light. Water vapor absorbs some infrared and parts of the visible spectrum. Ozone high in the stratosphere absorbs most ultraviolet light, protecting life on Earth's surface from harmful UV radiation. Without the ozone layer, the sun's ultraviolet light would sterilize the planet's surface, making complex life impossible. The photons that make it through the atmosphere are the ones that happen to hit wavelengths the atmosphere transmits relatively well, a narrow window we call the visible spectrum. Now here's where things get interesting for starlight. Stars don't just emit one wavelength. They emit a spectrum, a range of wavelengths determined by their surface temperature. When starlight enters the atmosphere, different wavelengths are scattered and absorbed to different degrees. The net effect is that stars appear slightly dimmer than they would from space, and their colors are subtly shifted. But there's another effect, one more immediately noticeable: twinkling. Stars twinkle because the atmosphere is not uniform. It's full of pockets of air at different temperatures, and densities constantly moving and swirling. When starlight passes through these turbulent layers, it gets refracted, bent slightly in random directions. From your perspective on the ground, this makes the star's position appear to shift rapidly, and its brightness fluctuates. Sometimes multiple pockets of turbulence line up, focusing the light and making the star brighter. Other times, they defocus it, making it dimmer. This happens several times per second, creating the twinkling effect. Interestingly, planets don't twinkle as much as stars. Why? Because planets, being closer to Earth, appear as tiny disks rather than points of light. The different parts of the disk are affected by different turbulence cells, and these effects average out, stabilizing the planet's appearance. Stars, being so distant, appear as true point sources. There's no disk to average over, so turbulence causes dramatic variations in brightness and position. Astronomers hate twinkling. It blurs images, reduces the sharpness of telescopes, and limits what we can see. This is why many professional observatories are built on high mountains and dry climates. Places like Mauna Kea in Hawaii, the Atacama Desert in Chile, and the Canary Islands. High altitude means less atmosphere to look through. Dry air means less water vapor, which absorbs infrared light and adds turbulence. But even the best mountaintop observatories have to contend with atmospheric distortion. In the 1990s, astronomers developed adaptive optics, a technology that compensates for atmospheric turbulence in real time. A laser is shot into the sky, creating an artificial star by exciting sodium atoms in the upper atmosphere. The telescope measures how this artificial star's light is distorted by turbulence, then uses a deformable mirror to counteract the distortion, effectively removing the twinkle. With adaptive optics, ground-based telescopes can achieve resolutions approaching those of space telescopes, despite looking through the atmosphere. But most of us aren't using adaptive optics. We're just looking up with our eyes, and our eyes are remarkable instruments in their own right. The human eye is a biological optical system refined over hundreds of millions of years of evolution. Light enters through the cornea, a transparent dome on the front of the eye. The cornea does most of the focusing, bending light inward. Then the light passes through the pupil, the dark opening in the center of the iris. The iris controls the pupil's size, dilating in darkness to let more light in, contracting in brightness to protect the retina. Behind the pupil is the lens, a flexible structure that fine-tunes the focus. Muscles around the lens can change its shape, allowing you to focus on objects at different distances. This process, called accommodation, happens automatically and almost instantaneously. Finally, the light passes through the vitreous humor, a clear gel filling the eye's interior, and strikes the retina at the back of the eye. The retina is where light becomes a signal. It's a thin layer of tissue packed with photoreceptor cells, specialized neurons that convert light into electrical impulses. There are two main types of photoreceptors, rods and cones. Rods are incredibly sensitive and work well in low light, but they don't detect color. They're responsible for your night vision, your ability to see in near darkness. Cones are less sensitive but detect color. There are 3 types of cones, each sensitive to different wavelengths. Short wavelengths appear blue, medium wavelengths appear green, and long wavelengths appear red. Your brain combines signals from all three cone types to create the full spectrum of colors you perceive. Here's something most people don't realize. You have about 120 million rods and only about 6 million cones. Rods vastly outnumber cones, and they're concentrated in the periphery of your retina. Cones are concentrated in the center, in a small region called the fovea, which is responsible for your sharpest, most detailed vision. This is why you see colors best when you look directly at something, but you're more sensitive to faint light in your peripheral vision. When you look at a faint star, your cones often can't detect it. The light is too dim. But if you look slightly to the side, the star appears brighter because you're using your peripheral vision, where rods dominate. Astronomers call this technique averted vision, and it's a useful trick for seeing faint objects. Ancient astronomers knew this instinctively. They knew that looking directly at faint stars made them disappear, but glancing sideways made them visible. Now, let's talk about what happens when a photon actually hits a rod or cone cell. Inside these cells are molecules called photopigments. In rods, the photopigment is rhodopsin, sometimes called visual purple. When a photon strikes rhodopsin, it causes a chemical change, breaking apart a molecule called retinal. This triggers a cascade of reactions that amplify the signal. A single photon absorbed by a single rhodopsin molecule can trigger a response strong enough for your brain to potentially detect. Your eyes are quantum detectors capable of registering individual photons under ideal conditions. Scientists have tested this. In experiments conducted in the 1940s, researchers Selig Hecht, Simon Schleyer, and Maurice Pirenne found that human subjects could detect flashes containing as few as 5 to 7 photons, with some evidence suggesting detection of even fewer. Your eyes are among the most sensitive light detectors in the biological world, capable of operating across an astonishing range of brightness levels, from the faintest starlight to the glaring noon sun, a range spanning about 10 billion to 1. But this sensitivity comes with limitations. Rhodopsin, once it's been activated by light, needs time to regenerate. This is why your eyes take time to adapt to darkness. When you step from a bright room into a dark one, your pupils dilate immediately, but your rhodopsin is mostly depleted. It takes about 20 to 30 minutes for your rhodopsin levels to fully recover, a process called dark adaptation. This is why astronomers use red lights when working at night. Red light is dim enough that it doesn't deplete rhodopsin as quickly as white or blue light, allowing them to preserve their night vision while still being able to see their equipment. There's another strange limitation. You can't see the color of faint stars. Even though stars emit different colors based on their temperature, when you look at stars with your naked eye, most appear white or slightly bluish. Only the brightest stars like red Betelgeuse or blue Rigel show obvious color. This is because faint stars don't emit enough light to activate your cones. You're seeing them with your rods, which are colorblind. The color is there, the photons carry the wavelength information, but your biology filters it out. Cameras and telescopes don't have this limitation. A camera can collect light over minutes or hours, accumulating photons, until there are enough to create a detailed, colorful image. This is why astronomical photographs show galaxies and nebulae in vivid colors, while those same objects appear gray or faintly colored through a telescope eyepiece. The colors are real, the photons are carrying that information, but your eyes simply aren't sensitive enough to collect enough photons to perceive them. There's a deeper truth here. Your eyes are not neutral observers. They're tuned, optimized, shaped by evolution to detect certain wavelengths and ignore others. Bees see ultraviolet light, allowing them to see patterns on flowers invisible to us. Some snakes see infrared, detecting the heat signatures of warm-blooded prey. Some mantis shrimp have 12 types of color receptors compared to our 3, allowing them to perceive colors we can't even imagine. Our view of the universe is constrained by our biology. We see only what our eyes were evolved to see, a narrow slice of the electromagnetic spectrum filtered through our atmosphere, interpreted by our brains. And yet, from this narrow window, we've learned so much. We've discovered that stars come in different temperatures and sizes. We've measured cosmic distances. We've understood the life cycles of stars, the structure of galaxies, the expansion of the universe, all from analyzing the light that makes it through the atmosphere and into our instruments. Imagine what we're missing, what wavelengths carry information we can't detect, what phenomena occur beyond the reach of our senses and our technology. The atmosphere is both a blessing and a curse. It protects us, filters harmful radiation, makes the sky beautiful with its scattering and colors. But it also obscures, distorts, limits what we can see. This is why we build space telescopes, why we send instruments beyond the atmosphere to observe the universe without this final barrier. The James Webb Space Telescope, the Hubble Space Telescope, and others like them see the universe as it truly is, unfiltered by air and water, vapor, revealing details invisible from the ground. But for most of human history, we had only our eyes and the atmosphere. And still we learned, still we wondered, still we looked up and asked questions. What are those lights? Where do they come from? How far away are they? And slowly over centuries we found answers. Not complete answers, not final answers, but answers enough to transform our understanding of our place in the cosmos. So, when a photon finally strikes your retina after its incomprehensible journey, what happens? A molecule changes, a signal fires, a neuron activates, and somewhere in your brain, in the visual cortex, a pattern emerges. You perceive light, you see a star. That ancient photon, that traveler from distant time and space, has completed its journey. And in completing it, it's connected you to something vast and far away, something you'll never touch, but can for a fleeting moment truly see. Yet seeing is not the same as understanding. The photon delivers its message, but what does that message mean? What are we actually observing when we observe the stars? That question, the deeper question of what starlight reveals about the nature of reality itself, is where we're heading now. When you look at the night sky, you think you're seeing the universe as it exists right now, but you're not. You're looking at a museum, a collection of moments from different eras, all displayed simultaneously. Each point of light is a timestamp, a frozen instant from the past. The sky is not a photograph of the present. It's a collage of history, and the deeper you look, the farther back in time you travel. This isn't metaphor, it's physics. Light has a speed, and that speed creates a fundamental limitation. Information cannot travel faster than light, which means we can never see distant objects as they are now. We can only see them as they were when their light left them. The night sky is a timeline spread across distance, and every star, every galaxy, every glowing nebula is a window into a different moment of cosmic history. Let's start with something relatively close. The moon is about 400 kilometers away. Light from the moon takes roughly 1.3 seconds to reach Earth. When you look at the moon, you're seeing it as it was 1.3 seconds ago. Not a significant delay, barely noticeable, but real nonetheless. If the moon suddenly vanished, you wouldn't know for 1.3 seconds. You'd see it sitting peacefully in the sky for another moment before it disappeared from view. The present moment on the moon and the present moment on Earth are not synchronized. They're separated by the travel time of light. The sun is about 150 million kilometers away, roughly 8 light minutes. When you see the sun, you're seeing it as it was 8 minutes ago. If the sun suddenly stopped shining, we wouldn't notice for 8 minutes. The light already in transit would continue arriving, and we'd bask in sunlight from a dead star for those final moments. Then abruptly darkness. And 8.3 minutes after that, we'd feel the gravitational effects as well, since gravity also propagates at the speed of light. Earth would stop orbiting and begin moving in a straight line, flying off into space. Of course, the sun won't suddenly stop shining, but the thought experiment reveals something profound. There is no universal present. The idea of now depends on where you are and what you're looking at. If you could instantly teleport to the sun, you'd find it in a state 8 minutes ahead of what we're seeing from Earth. but you can't teleport. You can't access the sun's present from here. All you can access is its past, carried to you by photons traveling at finite speed. Now, let's go farther. Jupiter, when it's at its closest to Earth, is about 33 light minutes away. Saturn is around 80 light minutes. Neptune, the most distant planet in our solar system, is about 4 light hours away at its closest. When you look at Neptune through a telescope, you're seeing it as it was 4 hours ago. Pluto, though no longer classified as a planet, is roughly 5.5 light hours away. By the time its light reaches us, Pluto has already moved significantly in its orbit. We're chasing a ghost. Voyager 1, the most distant human-made object, is currently over 24 light hours away, beyond the heliopause traveling through interstellar space. Commands sent to Voyager 1 take over 24 hours to arrive. Responses take another 24 hours to return. A conversation with Voyager 1 requires nearly 2 days for a single exchange. The spacecraft is slipping away into a time delay we can barely manage. But let's leave the solar system entirely and return to the stars. As we discussed earlier, Proxima Centauri is 4.24 light-years away. Alpha Centauri A and B, its companions, are about the same distance. The light we see from these stars tonight left them in 2021. Sirius, 8.6 light-years away, shows us 2017. Vega, 25 light-years, shows us 2001. Arcturus, one of the brightest stars in the spring sky, is about 37 light-years away, showing us the late 1980s. Aldebaran, the orange eye of Taurus the Bull, is about 65 light-years away. The light from Aldebaran left around 1960 during the Cold War, the space race, the early days of the Civil Rights Movement. When you look at the constellation Orion, you're seeing stars from wildly different eras. Rigel, the blue supergiant marking Orion's foot, is roughly 860 light-years away. The light we see left around the year 1165 during the Crusades before the Magna Carta, before Genghis Khan united the Mongol tribes. Bellatrix, the star on Orion's shoulder, opposite Betelgeuse, is about 250 light-years away, showing us the 1770s, the era of the American Revolution. These stars appear to be neighbors in the sky, but they're separated by centuries of light travel time. They're not close in space, and they're certainly not close in time. And then there are the galaxies. The Andromeda Galaxy, as we've noted, is 2.5 million light-years away. But Andromeda is relatively close. The Triangulum Galaxy, another member of our local group, is about 3 million light-years away. The light we see from Triangulum began its journey during the Pliocene epoch, when early hominids were just beginning to diverge from other primates. Australopithecus existed, but Homo did not. That photon traveled through space while our entire genus evolved. Consider the Virgo cluster, a massive collection of galaxies about 50 to 60 million light-years away. The light from those galaxies left during the Paleocene epoch shortly after the dinosaurs went extinct. Mammals were diversifying, filling ecological niches left empty by the extinction event. Primates existed, but they were tiny tree-dwelling creatures, nothing like modern humans. And while those early primates scurried through ancient forests, photons were leaving distant galaxies, beginning a journey that would outlast entire lineages of life on Earth. The Coma cluster, even farther, is about 320 million light-years away. The light from the Coma cluster left during the Carboniferous period, the age of giant insects and the first reptiles. The supercontinent Pangaea hadn't formed yet. Life had only recently colonized land. The photons we're seeing from those galaxies tonight are older than dinosaurs, older than mammals, older than flowers. But we can go deeper still. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky in the constellation Ursa Major. The patch was so small, it would take 12.7 million such patches to cover the entire sky. They left the telescope pointed at this dark region for 10 days, collecting every photon that arrived. The result was the Hubble Deep Field, an image containing about 3,000 galaxies, some of them among the most distant objects ever observed at the time. Many of those galaxies are over 12 billion light years away. The light from them left when the universe was less than 2 billion years old, just 14% of its current age. In 2004, Hubble did it again, creating the Hubble Ultra Deep Field, going even deeper. And in 2012, the Hubble Extreme Deep Field pushed further, still revealing galaxies so distant their light has been traveling for over 13 billion years. These galaxies formed when the universe was only a few 100 million years old, during a period called the Epoch of Ionization, when the first stars and galaxies were lighting up the cosmos, ionizing the hydrogen gas that filled intergalactic space. What do these ancient galaxies look like? Small, irregular, chaotic. They haven't had time to settle into the elegant spiral or elliptical shapes we see in nearby galaxies. They're still forming, still merging, still violent with star formation. Many of them no longer exist in the forms we're seeing. Over billions of years, they've collided with other galaxies, merged, evolved into completely different structures. We're seeing their infancy long after they've grown up. And there's one more layer, the deepest of all. The cosmic microwave background, or CMB, is the oldest light we can ever see. It comes from a time about 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form and light to travel freely for the first time. Before that moment, the universe was opaque, a hot plasma, where photons couldn't travel far without being absorbed and re-emitted. But when atoms formed, the plasma cleared and light streamed out in all directions. That light has been traveling ever since, redshifted by cosmic expansion from visible wavelengths into microwaves. It fills the entire sky, a faint glow, at a temperature of about 2.7 Kelvin, just barely above absolute zero. When you observe the cosmic microwave background, you're looking back 13.8 billion years, seeing the universe as it was in its infancy. This is the edge of the observable universe, not because there's nothing beyond it, but because light from beyond it hasn't had time to reach us yet. The CMB is the ultimate time capsule, the earliest snapshot of the cosmos we can access. Beyond it lies a realm we cannot see, cannot know, separated from us not by distance alone, but by the finite speed of light and the finite age of the universe. So, when you look at the night sky, you're not seeing a single moment. You're seeing a cascade of moments layered at different distances. The moon from 1.3 seconds ago, the sun from 8 minutes ago, Sirius from 2017, Betelgeuse from 1382, Andromeda from 2.5 million years ago, distant galaxies from billions of years ago, and the cosmic microwave background from 13.8 billion years ago. Each depth is a different chapter in the history of the universe, and all of them are visible simultaneously. This creates a strange philosophical problem. If every point in space sees a different past, depending on what it's looking at, is there such a thing as a universal present? According to relativity, no. Time is not a single universal flow. It's local relative dependent on your reference frame and your position in space-time. Two events that are simultaneous for one observer might not be simultaneous for another observer moving at a different speed or in a different gravitational field. Einstein described this using the concept of light cones. Imagine a point in space-time, a specific location at a specific moment. The future light cone contains all the events that could be influenced by that point, all the places light could reach traveling forward in time. The past light cone contains all the events that could have influenced that point, all the places light could have come from traveling backward in time. Events outside the light cones are causally disconnected. They can neither influence nor be influenced by the point in question. They exist in a kind of limbo, a region where simultaneity is ambiguous and relative. This means the universe doesn't have a single timeline. It has countless overlapping timelines, each one local to a particular observer. Your present is not my present if we're in different locations or moving at different speeds. And the farther apart we are, the more our presents diverge. At cosmic distances, the concept of now becomes almost meaningless. One of the most common mistakes people make is thinking that because we can see distant galaxies, we can see them as they are now. We can't. We can only see them as they were. This leads to a subtle but important realization. The universe we observe is not the universe that exists. It's a historical record, a light-based archive of what was. The actual present state of the universe is unknowable to us. All we have is the past delivered photon by photon across the vast distances of space. Another mistake is thinking time flows the same way everywhere. It doesn't. Near a black hole, time slows down due to extreme gravitational time dilation. An observer far from the black hole would see someone falling toward the event horizon, moving slower and slower, their clock ticking more and more sluggishly, never quite reaching the horizon from the outside observer's perspective. Meanwhile, the infalling observer feels time passing normally and crosses the horizon in finite time by their own clock. Time is not universal. It's relative malleable, shaped by gravity and motion. What does all of this mean for our understanding of the cosmos? It means the universe is stranger than we intuitively grasp. It means the night sky is a time machine, the only one we have. We can look back billions of years just by pointing a telescope at distant galaxies. We can study the early universe, the formation of stars, the evolution of galaxies, all by collecting ancient light. Cosmology is archaeology, and photons are the fossils. But it also means there's humility built into the structure of reality. We can never see the whole universe at once. We can never know the present state of distant places. We're trapped in our light cone, receiving news from the past, sending signals into the future, but never experiencing a universal now. The cosmos is too large light too slow, and time too local. We see only what light allows us to see, and light shows us history, not the present. Yet from this limited view, we've learned so much. We've measured the age of the universe. We've discovered its expansion. We've traced the formation of galaxies, the life cycles of stars, the synthesis of elements. We've found planets around other stars, detected gravitational waves from colliding black holes, and mapped the distribution of dark matter. All from studying light, from analyzing the messages carried by photons across unimaginable distances and times. The universe is a storyteller, and light is the language. Every photon is a word, every spectrum, a sentence, every image, a paragraph in a cosmic narrative billions of years in the telling. And we improbable beings on a small planet orbiting an average star have learned to read that language. We've learned to listen to the universe speaking in light. And in listening, we've discovered not just the universe's history, but our own origins within it. Because the ultimate truth of Starlight isn't just about distance or time. It's about connection. Every atom in your body was forged in the heart of a star that died before the sun was born. The carbon, oxygen, nitrogen, calcium, iron, every element heavier than helium, came from stellar nucleosynthesis and supernova explosions. You are quite literally made of stardust. And when you look at starlight, when you see those ancient photons arriving from distant suns, you're witnessing the same process that created you. The universe looking at itself. Stardust observing starlight. That's what we turn to now in the final moments of this journey, the realization that the observer and the observed are not separate, but profoundly beautifully connected. There's a peculiar comfort in knowing you're made of stars, not metaphorically, not poetically, but literally. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged inside stars that lived and died billions of years ago. You are the universe experiencing itself stardust, that has learned to think, to wonder, to look up at the night sky, and recognize its own origins. Let's trace this story backward. Every breath you take contains oxygen atoms. Those atoms weren't present at the Big Bang. The early universe contained only hydrogen, helium, and trace amounts of lithium. Everything else, every element on the periodic table heavier than those three, was created later inside stars. Oxygen forms in the cores of massive stars during the later stages of their lives when they've exhausted their hydrogen and helium and begin fusing heavier elements. When these stars explode as supernovae, they scatter oxygen and other elements into space, seeding the interstellar medium with the raw materials for new stars, new planets, new life. The iron in your blood has an even more dramatic origin. Iron is the end of the line for stellar fusion. When a massive star's core accumulates enough iron, fusion stops being energy positive and becomes energy negative. The core can no longer support itself against gravity. In less than a second, the core collapses, then rebounds in a catastrophic supernova explosion. During that explosion, the intense heat and pressure create elements heavier than iron, gold, platinum, uranium through a process called rapid neutron capture. Every gold ring, every piece of jewelry, every precious metal on Earth was born in the death throes of a star. In 2013, astrophysicists at the Harvard-Smithsonian Center for Astrophysics published calculations estimating that about half of the atoms in your body came from galaxies other than the Milky Way. These atoms were ejected from distant galaxies by supernova-driven winds, traveled through intergalactic space for millions of years, and eventually found their way into the gas cloud that would become our solar system. You're not just made of stardust. You're made of extragalactic stardust, cosmic immigrants from distant realms. Think about that for a moment. The calcium in your bones might have come from a supernova in the Andromeda Galaxy. The carbon in your DNA might have formed in a red giant in the Triangulum Galaxy. You are in a very real sense an amalgamation of the universe's history. Every element tells a story, and those stories span billions of years and trillions of kilometers. You are a living archive of cosmic events. The astronomer Carl Sagan famously said, "We are made of star stuff. We are a way for the universe to know itself." It's one of the most quoted lines in science, and for good reason. It captures a profound truth about our existence. The universe is not something separate from us, something we observe from the outside. We are part of it, woven into its fabric, made from its substance. And through us, through our consciousness and curiosity, the universe has developed the ability to study itself, to understand its own history, its own structure, its own fate. When you look at Starlight, you're closing a circle. The atoms in your eyes were created in stars. The photons entering your eyes came from stars. The process of seeing connects two products of stellar alchemy, photon and observer, across the void. It's a reunion of sorts, scattered pieces of the cosmos finding each other again after eons apart. But there's more to this connection than chemistry. There's also time. The light you see from distant stars and galaxies is ancient, often older than Earth itself. When you observe a galaxy 10 billion light-years away, you're seeing it as it was when the universe was only 3.8 billion years old, less than a third of its current age. Our solar system didn't exist yet. The Milky Way looked different. Many of the stars whose remnants now make up your body hadn't even formed. You're looking back to a time before you, in any form, could have existed. And yet, here you are. Here we are. Conscious beings capable of understanding this chain of connections, capable of tracing our origins back through supernovae and galaxy formation and cosmic expansion, all the way to the Big Bang itself. It's staggering when you really think about it. We are the universe's way of understanding where it came from. There's a concept in cosmology called the anthropic principle. It comes in different forms, but the weak version essentially says that the universe must be compatible with the existence of observers, because if it weren't, we wouldn't be here to observe it. The strong version goes further, suggesting that the universe must have properties that allow consciousness to develop. Whether you accept these principles or not, they raise an interesting question. Is it a coincidence that the universe is capable of producing beings who can understand it? Some scientists argue Yes, it's just chance. The universe has the properties it has, and we happen to exist in a region and an era where those properties allow for life and consciousness. Other universes, if they exist, might have different properties and no observers at all. We don't know. What we do know is that this universe, our universe, has given rise to complexity to stars and planets and chemistry and biology, and eventually to minds capable of pondering their own existence. The physicist John Wheeler once proposed a participatory universe. The idea that observers play a role in bringing the universe into being, not in a mystical sense, but through the act of observation collapsing quantum possibilities into definite states. It's a controversial idea, and most physicists don't take it literally, but it hints at something deeper. The universe and the observer are not separate. They're part of the same system, the same unfolding process. You are not watching the universe from the outside. You're part of the show. When photons from a distant star finally reach your eye, their journey ends. But in ending, they complete something. They deliver information across time and space, connecting you to an event that happened perhaps millions or billions of years ago. In that moment, past and present touch. The star that emitted those photons may no longer exist, but its light persists, carrying forward a message that says, I was here. I burned. I created elements. And now, across all this distance and time, a piece of me has reached you. There's a bittersweet beauty to this. Every photon that arrives is also a photon lost. Once absorbed by your eye, it's gone, its energy converted into a neural signal. The light that traveled for centuries or millennia ends in a fraction of a second, transformed into an electrical impulse interpreted by your brain as a point of light in the darkness. That particular photon's journey is over. It will never travel again. But in that ending, it accomplishes something remarkable. It allows you to see, to know, to connect with the cosmos. And the universe doesn't stop. Even as some photons complete their journeys, new ones are being born. Right now, in the cores of stars across the galaxy, fusion reactions are creating fresh photons. They're beginning the long struggle to escape their stellar prisons, bouncing through dense plasma, zigzagging toward the surface. Someday, perhaps, in 100,000 years, they'll break free and begin the crossing. And if Earth still exists, if there are still eyes to see, those photons might complete journeys that started today. The cycle continues. Stars are born from clouds of gas enriched by previous generations of stars. They live. They fuse elements. They create light. They die, scattering their creations back into space. New stars form from the debris. New planets. New opportunities for complexity, for chemistry, for life. The universe recycles itself, endlessly transforming, endlessly creating, endlessly connecting past and future through the medium of light. You are part of this cycle. The atoms that make up your body will someday return to the universe. When you die, those atoms will disperse. Some will remain on Earth, incorporated into other living things cycling through the biosphere. Others, over geological timescales, might escape Earth's gravity and drift into space. And in the far, far future, billions of years from now, when the sun expands into a red giant and consumes the inner planets, even those atoms will be cast back into the cosmos, ready to be incorporated into new stars, new worlds, new possibilities. There's a timelessness to this. You are temporary, a brief configuration of atoms that will dissolve. But the atoms themselves are ancient and will endure long after you're gone. You're a temporary pattern in an eternal dance, a fleeting arrangement of stardust that for a brief moment can think and feel and wonder. And in that wondering, you touch something infinite. So, what does it mean to see starlight? It means you're witnessing the end of a journey that might have begun before you were born, before your species existed, before your planet formed. It means you're receiving a message from the past delivered by the universe's fastest messengers across distances your mind cannot truly comprehend. It means you're participating in a cosmic conversation, a dialogue between matter and energy, between space and time, between creation and perception. And perhaps most importantly, it means you're not alone. You're connected to everything, to the stars that made you, to the light that reaches you, to the vast, ancient, ever-expanding universe that gave rise to both. You are not a separate observer looking at the cosmos from the outside. You are the cosmos looking at itself, understanding itself, marveling at its own existence. Do you feel that connection? When you look up at the stars, do you sense the enormity of it all, the improbable chain of events that led to this moment? Do you here now, seeing light from distant suns? It's okay if you don't. It's okay if it feels too large, too abstract. But maybe the next time you see a star, you'll remember. You'll remember that the light took years or centuries to reach you. You'll remember that you're made of the same stuff as the stars. You'll remember that you're part of something vast and beautiful and incomprehensibly old. The journey of light doesn't end when it reaches your eye. In a sense, it continues. It continues in your thoughts, in your understanding, in the meaning you make from it. The photon is absorbed, yes, but the information it carried persists. You know something now you didn't know before. You've been changed, however slightly, by the arrival of that ancient light. And in being changed, you carry the story forward. This is what we've been exploring tonight, the journey of light from its violent birth in the core of a star, through its long imprisonment inside stellar plasma, its escape into space, its solitary crossing of cosmic distances, its encounter with gravity and expansion, its final passage through Earth's atmosphere, and at last, its absorption by your eye. Every step is a marvel. Every stage reveals something profound about the nature of reality, time-space, and our place within it all. Light is patient. It doesn't hurry. It doesn't worry. It simply goes at the only speed it knows, carrying information, connecting distant parts of the universe, bridging gaps that seem unbridgeable. And we, improbable as we are, have learned to read the messages light carries. We've learned to decode its wavelength measure, its intensity, analyze its spectrum, and from these clues we've reconstructed the history of the cosmos. We've learned where we came from, what the universe is made of, how old it is, how it's evolving, all from studying light. So, as you drift towards sleep tonight, if you drift at all, remember this. The stars you see are not just lights in the sky. They're beacons from the past, messages from distant times and places, evidence of processes that created you. You are not separate from the stars. You are continuous with them, part of the same story, the same unfolding cosmic narrative. And the light that reaches your eyes after journeys lasting years, or millennia, or millions of years, has come all this way to remind you of that connection. Sleep well, knowing you are part of something infinite. Dream gently knowing the universe dreamed you into being. And when you wake and look up again, know that the stars are still there, still shining, still sending their light across the void, patiently waiting for someone to see. Thank you for joining me on this quiet journey through the cosmos, through time, through the nature of light and vision and existence itself. I hope it brought you some sense of wonder, some peace, some connection to the vast and beautiful universe we're all a part of. If these gentle explorations speak to you, there are more to come, more stories told, softly in the dark, more science wrapped in wonder, more reasons to pause and look up and remember how extraordinary it all is. Until the next quiet night finds you rest well. The stars will still be there carrying their ancient light toward you, one photon at a time, across all that distance, all that time, just to reach your eyes and remind you you are made of stars and you are home. Good night.